Hello, welcome to the second lecture of Phys 1101, and in this lecture we'll be looking at significant figures, which is a topic I find confuses a lot of students. I'm going to start with a claim. My age is 1.374969642075141119 times 10 to the 9 seconds. So the question is, do you believe me? Well, you might start by wondering just how old that is in years, and you can go ahead and figure it out if you want. But the main point is, if you just note that this is times 10 to the 9 seconds and count digits, you'll find that the ones place is there, right? So there's 2 seconds sitting in that digit. And so all these digits are representing smaller and smaller fractions of a second. And again, if you count digits, you'll find that I've just given you my age to a precision of 10 nanoseconds. Now, I actually don't know what time of day I was born, but maybe there's a hospital record somewhere that says. But I'm pretty sure that my time of birth in that hospital record will not be recorded to the nearest 10 nanoseconds. So there's absolutely no way that I know all these digits. In fact, I really probably don't know anything past about here, and even at that point, it'll be out of date in another hour. So all those extraneous digits are junk, complete garbage. I don't know them. I shouldn't quote them. So the significant figures are the known digits in a measurement. It's not the number of digits after the decimal. It's not the number of digits we've written down. And to understand sort of the difference between the known digits, the number of digits after the decimal, and the number of digits we've written down, you need to understand this idea of placeholder zeros, which are there to just establish the order of magnitude of the number, but aren't significant digits. So let's look at some examples. So here's the first example. Look at that number. It has 5 digits after the decimal place, and there are 6 digits written down. But I'll tell you, it has only 4 significant figures. And the point is, these 2 zeros here are to tell you that the first significant figure, this 3, is in the hundredths of a second place. So they're there to establish the order of magnitude. Everything after that is a significant figure. I could have written 3.501 times 10 to the negative 2 seconds, right? And now it's clearer that there are 4 significant figures. And in general, if you want to make it really clear how many significant figures you have in a number, you should write it in scientific notation. So now let's look at this one. These 862 are almost certainly significant figures. These zeros are placeholder zeros. Or are they? You see, it's unclear. We don't know whether we've made this measurement to a precision of plus or minus 1 kilometer, and it just happened to come out as a fairly round number, 862,000, or whether we're writing these zeros here because we don't know these digits, but we do know we've got 862,000 and something. So this is unclear. This would be far clearer if we were to write it in scientific notation. Now, if we really only know those 3 digits, we can write it this way. But on the other hand, if we've actually carried this measurement out to a precision of 1 kilometer, we can write it this way. And similarly, if we'd only carried it out to a precision of, say, 100 kilometers, we could add 1 more zero, because that would be a significant figure. So there are some rules, and they actually are not really important. And the reason is that for real measurements, it's always better to write down an uncertainty. Okay, and so you need to know something about the precision of the measurement, and we'll see later how you figure out what the uncertainty is in a measurement. But when you don't know the uncertainty, but for whatever reason you know the number of significant figures, there are some rules for how to propagate the sig figs through calculations so that you know how many significant figures you have in a final answer. Let's look at these rules and do a couple of examples to illustrate them. Here's the multiplication and division rule. The number of sig figs of the answer should match the number of sig figs of the least precisely known number used in the calculation. What do I mean least precisely known? What I mean is the one with the fewest sig figs. So we can do that over here. Let's just take those numbers and plug them into a calculator. Oops, where'd it go? 3.67 times 124.6, and we get 457.282. 457.282. Now, notice that this one has 3 sig figs, this one has 4 sig figs. We take the one with the fewest sig figs, so 3, and so we should have 3 sig figs in our answer. The rest of this is junk. We don't actually know those digits, and so we round off, 0.2 rounds down, so 457 is what we get there. Now, a lot of students get more mixed up with the addition and subtraction rule. The number of places after the decimal, not sig figs, the number of places after the decimal in the answer should match the places in the number with the fewest digits after the decimal. Okay, so notice we're not talking about sig figs, we're talking about places after the decimal. And you can understand it if you think about this. When you first learned to do a subtraction like this, you would have learned to put zeros here. Okay, however, with data, that's not correct, because with data, we haven't written those digits not because they're 0, we haven't written them because we don't know what they are. So these are question marks. Okay, and question mark minus 6 is question mark, right? So that's why this rule happens. In other words, we're saying the last digit we actually know anything about is here. And if you now carry out the subtraction, what you should really do is round this, if you're going to do it by hand, ignoring these digits, right? So you do 1807.3 minus 4 point, that's going to round to 6. And you get 1802.7. Try it out if you don't believe me. Now, you don't have to do it by hand like that. If you're doing it in a calculator, you just go ahead and enter everything in. 1807.3 minus 4 point, and I'll put it all in, 576. And we get, so the calculator gives 1802.724, 1802.724, but now we look and we say I need to round to one place past the decimal place because that's the number of digits past the decimal place of the number with the fewer, and so those are gone. We round off to 1802.7 and we're done. So if we have a measurement and we've written it down as 1807.3, what it might be is a measurement where we believe the actual value lies in the range between 1807.25 and 1807.35, or what you would write down as 1807.30 plus or minus 0.05. So if that's how we interpret that number, then this subtraction, and if we also interpret this other number the same way, you can think of it as having a lower limit, which would be 1807.25 minus 4.57, and everything after this doesn't matter. Right, so I'm not going to worry about writing it after there. or an upper limit of 1807.35 minus 4.5, and again I'll stop writing at the 7. So if you just carry out those two subtractions, you get 1802.67 and 1802.87. So there are our upper and lower limits. So in other words, our answer, we believe our answer lies in the range between 1802.67 and 1802.87. Now just think about what that means. We believe then that the second digit, or this first digit after the decimal place, is a 6, 7, or 8. We think it's one of those. Now, at first sight, you might be tempted to say, oh, and we think this last digit is a 7. But no, remember, it lies, the answer lies anywhere in this range. So it could be 0.68, 0.69, 0.7, 0.71, 72, right? We really have no idea what this digit is. It could be anything. And so that's why now, having done this subtraction, we keep the digit that we've written down up here as a 7, because we know something about it. It's a 6, 7, or 8 if you interpret the subtraction this way, whereas this next digit we know absolutely nothing about, and so we shouldn't write it.